In the previous discussion, we have talked about enantiomers having similar chemical properties. Physical and chemical properties. They have the same boiling point, same melting point, and same density. And it makes sense because their properties are actually determined by intermolecular interactions, right? So both the enantiomers will have the same intermolecular interaction, so they will behave exactly the same in terms of their physical properties, right? However, they do exhibit different behavior when exposed to what is called as plane polarized light. Okay, so if you normal light is what is shown over here, but when it passes through a polarizer, this is the unpolarized light, and when it passes through a polarizer, what we get is a plane polarized light where you have the light vibrating in one direction. So when that light is passed through a sample tube which contains a compound which is chiral, then it is seen that they are able to rotate this plane polarized light either to the left or to the right. Okay, so the difference in the enantiomers is that if one enantiomer rotates the plane polarized light to the right, then the other enantiomer will rotate the plane polarized light to the left with the same magnitude. Okay, so those compounds which can rotate the plane polarized light are what are called as optically active compounds. Okay, so we call them as optically active. Okay, here we have the statement here, optically active compounds. This was actually also supported by Louis Pasteur's investigation of tartrate salts, where he led to the conclusion that optical activity is a direct consequence of chirality. That means if a molecule is chiral in nature, then that is the one that will be optically active. Okay, so if you look at enantiomers, if one enantiomer rotates the plane polarized light to the right to one direction, and then with a certain magnitude, and if the other enantiomer rotates the plane polarized light to the other direction, then if you have equal quantities of the same enantiomers, what do you think will happen? There will be no optical activity, right? Because 50% of the molecules will rotate the plane polarized light to the right, and 50% will rotate it to the left. So then you will not see any optical activity in that case, right? So those kind of mixtures which contain equal quantities of enantiomers are what are called as racemic mixture. Okay, all right, we can talk about that in a little bit. But here there is a more better depiction of the how the light passes through this polarimeter, and then you have the plane polarized light. This is a sample tube which contains your organic compound. If it is optically active, then you can see that the light is rotated, and if it is not optically active, then you don't see any rotation in the light. Okay, so we use these terms dextrorotatory and levorotatory to tell if it is rotating to the right or to the left. Okay, if it is clockwise to the right, we call it as dextrorotatory, and if it is anti-clockwise, it's called as levorotatory. Okay, but you have to be careful in noting this point that the dextro and levo are not related to R or S. Remember that R and S configurations were assigned only to distinguish one enantiomer from the other, right, in terms of naming. However, it's not related to their optical activity at all. So an R enantiomer could be dextrorotatory or levorotatory, and similarly an S enantiomer could be dextro or levo. You cannot predict that unless you perform the experiment where you take the plane polarized light and pass it through the sample tube and measure the magnitude of the rotation of the plane polarized light. Okay, so to illustrate the idea that what is optical activity, so for example, if I take this molecule, this is bromobutane. Okay, this is bromobutane, and if I draw the enantiomer of that, it will be this one, right? So both are bromobutane, but this one is R bromobutane and this one is S bromobutane. When these molecules are placed in the sample tube here, this enantiomer is able to rotate the light through minus 23.1 degrees. Okay, and what do you think? Can you predict how much will this rotate it to? To the same magnitude but to the opposite direction. Okay, so what is this value referring to? This is what is called as a specific rotation. Okay, so we use the term specific rotation to represent the optical activity. So how specific rotation is calculated by keeping the length of the cell and the concentration constant, and also using a constant using a light with a specific wavelength. Okay, in that way we are keeping some of the parameters the same and measuring only the rotation of the light with respect to the compound that's in the tube. Okay, so this what is representing the specific rotation, and that is what we are measuring it. Okay, so again the specific rotation of a compound is defined as the observed rotation under these specific conditions, standard conditions. We can call them as standard conditions. And what are they? That we are using a 1 gram per milliliter concentration of the solution, and the path length is 10 centimeter, and we are using a sodium vapor lamp with 589 nanometer as the wavelength. Okay, so we are keeping the concentration, the path length, and the wavelength of the light constant, and then we observe the rotation of the light, and that is what is called as the specific rotation. In this table, you can see the specific rotations of some compounds given here. Some of them have a 0 value, right? So why do you think chloroform has a 0 value? Now let me draw the structure of chloroform here. This is CH, Cl, Cl, and Cl. This is what chloroform is. Now can you think of the reason why chloroform is not optically active, or why is it giving a 0 value to the specific rotation? Simple, right? Because this doesn't have a chiral center. So no chiral center. You need to have 4 different groups in order to have a chiral center. So here there is no chiral center, so the molecule is optically inactive. Okay, then also same reason for acetic acid, because if you draw that out, there is no carbon atom with all 4 groups different. However, also remember that if you have a racemic mixture, just like I was talking to you about a little bit back, that if you have a racemic mixture, then also you will not be seeing any optical activity, because they contain equal amounts of the 2 enantiomers, right? So if one enantiomer rotates it to, say, for example, in this case 13.5 degree to the right, this will rotate to the same with the same magnitude to the left. So they are basically rendering the compound optically inactive. Okay, can you think of one more reason that a compound can be optically inactive? It will be a meso compound, right? Remember that meso compounds, even though they contain chiral centers, they are achiral, right? Because they have a symmetry in them. So that is what will result in the optical inactivity of meso compounds. Okay. There is a way by which you can actually separate out enantiomers. Let's talk about the separation of the enantiomers in the next video.